All right. Thank you for everyone for joining. Thank you for not only the conference, but my session. Today I'm going to talk about something called security chaos engineering. It's the adaptation of Netflix's chaos engineering to cybersecurity. I started pioneering this about 4 years ago when I was at United Health Group. I wrote the first open source tool in the space that sort of proved that that there was value and that it could be done. Below on the bottom, you'll see my Twitter information at Aaron Rinehart. If you want to reach out to me, feel free to reach out to me. And I'll go ahead and get started. Things I'm going to talk about. I'm going to talk a bit about combating complexity in software. I'm going to talk about chaos engineering. I'm also going to talk about resilience engineering and security. And I'm going to talk about what is this security chaos engineering thing. So a little bit of background on me. I'm the CTO and co-founder of a company called Verica. We are the creators of chaos engineering. My co-founder created chaos engineering at Netflix. His name is Casey Rosenthal. We build continuous verification products to continuously verify that the system works the way you think it does. I think it'll make more sense after my presentation. But also I have a few giveaways. I just finished the O'Reilly report on security chaos engineering. I'll be giving that away for free, as well as the O'Reilly book on chaos engineering. You have links at the end of the presentation. For further background information on me, I am the former chief security architect of United Health Group. I also have a background at the Department of Defense, Department of Homeland Security, and NASA. I'm a frequent author and speaker in the space on chaos engineering and its applications to security. I'm the author of the security chapter on the main animal book for chaos engineering, the O'Reilly one. And I'm also, like I said, I just finished the first O'Reilly report, or O'Reilly calls it a report, but it's still a book on security chaos engineering. All right, well, getting started here. So the basis of the problem we're trying to solve here is that incidents and outages and breaches are costly, but they seem to be happening more and more often. It's somewhat of an obvious problem. I haven't updated this slide in a while, just because it's, it seems like all the time there's just breaches and breaches and breaches and outages and outages and outages. We're almost becoming numb to it. And I think I have some theories on why they're happening more often, and I can posit some and give you some direction on what we can do to start combating this problem. So why is it they seem to be happening more often? Well, let's take a second and take a pause here. If you've never seen these diagrams, like the one you see in the two little circles on the right, each dot is a microservice. Okay, this is called the Death Star diagrams. So large-scale microservice architectures kind of look like this. It used to be that this was just Facebook, Apple, Netflix, Google that was creating these large-scale sort of microservice architectures. Well, it's really not. It's not just Amazon and Netflix anymore. Now everybody's sort of doing this. But when you combine the speed of CI/CD and DevOps, the scalability of public cloud, and microservice architectures, our systems are moving at such a size, speed, and scale that it creates a level of complexity that makes it difficult for humans to mentally model our system behavior, which makes it very difficult to build security if we can't understand the system inherently. So, furthermore, to illustrate that, if you look at this, this is a snapshot of a tool from Netflix called Visceral. Basically, what I want to show you here is every big circle is a microservice, every small dot is a request, and what I'm trying to illustrate is here in this sort of GIF here is that it's very difficult to ascertain what's going on at any given point in this architecture. Let alone in large-scale microservice architectures, we're not just worried about individual services. We're worried about the impact that multiple services have upon each other, because microservice architectures reflect the character traits of a complex system. Complex systems have nonlinear dynamics. So what does that mean? That means events or failure events, when bad things happen, it magnifies because everything is interconnected. People love to forget that microservices are not independent, they're dependent. But anyway, what I want to illustrate here is the level of complexity that we're dealing with. So things like continuous delivery, service meshes, cloud computing, APIs, auto canaries, blue-green deployments, circuit breakers. These sort of things, help. They're helping us deliver value to customer, to market, faster than we've ever been able to do it before. But it's also making it more difficult for us to ascertain what is actually happening with the system and keep that mental model fresh in our heads. From a security perspective, part of the problem with security is we're still mostly monolithic in how we design security solutions. I think that there's been a lot of growth in the software security community due to things like DevSecOps. More and more people are understanding software and understanding that we can't build stateful security in a stateless world, and that we can't continue to build expert types of systems because expert systems like Palo Alto firewalls are for example, you can't just grab one of those from GitHub and start rocking it. It requires some sort of domain knowledge to really understand and deploy it. So what is the answer to all this complexity, right? Well, the most logical conclusion would be to simplify, right? Well, software is officially taking over, right? And it's if you look on the right here, I stole this from James Wickett, but this is the new OSI model, right? Software, right? Well, software only ever increases in complexity, it never decreases in complexity due to our ability to constantly change it. Software is also one of the only human constructs that can fundamentally change after it's been delivered. You can't do that with a building, can't do that with a car. Well, Tesla's changing that model, but anyway, like I said, software only ever increases in complexity. But because there's an old saying in software that there's no problem there's no problem in software that can't be abstracted away. Well, at some point, those abstractions start to create a level of complexity that's very difficult to operate and continue to develop our systems. So what does this have to do with your systems? I'm getting there. How do we really, so the question I want to ask is, how well do you really understand your own systems? Well, I don't know why, I eventually came to this in my messaging and my thinking, but we love to forget how messy engineering is. It's a very messy discipline, and to illustrate, in the beginning, we love to think of our systems and designing them and operating them as you have the beautiful 3D Amazon, diagram that illustrates how the system works. You've got your code, you've got your Docker images, you're going to put it in staging and prod and your secrets management, you got everything figured out. Everything's figured out. Everything is clear, right? Well, in reality, our system never looks like this. It never reflects any of these characteristics. And let me tell you why, right? Is that after a few months or even a few weeks, sometimes even a few days, we start to learn about the difference between how our system actually functions and versus how we thought it did, right? And we start learning that through a series of surprises, our unforeseen events, outages, incidents. That's what I mean. That can be, so after first week, 1 week of going live, there's an outage on the payments API, you have to hard code a token. Of course, you go back and fix that. You just don't roll right in the next war room, right? Well, I find that most people actually just roll in the next war room. But then you have an expired certificate, or you have the incorrect pointers on from non-prod to prod. We slowly learn about what we didn't, wasn't exactly what we thought it was through these events. But the problem with this learning this way, right, is our system slowly drifts into a state of unknown. And what makes this even worse is that we're learning through pain, right? Costly pain, because customers are encountering often that kind of pain. But this is where chaos engineering comes in, and I'm going to expand on this, but chaos engineering is the ability to sort of proactively identify these unforeseen events and the drift between what you believe the system is in your head and how it actually functions in reality without incurring pain. And we're going to talk more about that. So in the end, our systems have become more complex and messy than we initially remember them. Because honestly, it's very difficult to keep track of all the changes in our heads. I don't think anybody really can. We have to abstract and simplify to make sense of things. So what does all this stuff have to do with security? Like I said, I'm getting around to it. I'm building, right? I also want to illustrate that the normal condition of any system is to fail. It's to fail. It's humans that keep it from failing. I illustrate that because in security we love to point the finger at the human, right? But security is a human construct, okay? And furthermore, we need failure to understand where we need to improve the security and how we can learn and improve and grow, to building a better and brighter security. So how do we typically discover when our security measures fail? Well, we typically discover when our security fails through a series of outages. Through security incidents. Typically, some kind of alert or some kind of sort of logging or observability metrics comes in and it throws an alert. An alert tells us something didn't work. Probably most likely from a security controller mechanism, and then we operate it. But the problem with that methodology is that it's very reactive, and security incidents are not effective measures of detection because it's probably too late at that point to really do a whole lot about it. You're more or less assessing damage control. Like I said before, no system is inherently secure by default. It's humans that make them that way, right? Safety, reliability, quality, resilience, right? These are all human constructs. So be careful anytime you point the finger at humans being the problem in security. It's also humans that are what's causing what's the solution, right? What's making things secure. Going on. During when things fail, people operate differently. So they also operate differently when we expect things to fail. So during an incident or outage or a war room, especially in terms of security incidents and outages, people freak out, right? People are worried about the name, blame, shame game, right? People are worried about it being their fault. They're worrying about being blamed for it. They're worrying about sometimes losing their job. Because what happens is within 15 to 30 minutes of the outage or incident is that you'll get a CEO or some senior executive, behind it and asking, hey, it's not about what happened. It's about get that thing back up and running. We're losing money, right? So the focus is trying to get the thing back to be operational, not what actually happened. The whole point here, and why I illustrate all these points, is that this is not a good learning environment. People are freaking out. They're worried. Their cognitive load is beyond reckoning. They're not able to look beyond the biggest problem in front of them, which could be losing their jobs. So we don't do chaos engineering here. We don't do it here. We do it here, right? We don't do it here. We do it here, right? We do it when nobody is freaking out, right? When there is no active war room, when there is no incident, right? We do it when when our eyes are wide open, when we can learn, and because it's a proactive exercise. We don't do it during war rooms, incidents, or outages. So chaos engineering. So what is this chaos engineering stuff? I'm sure you're hearing a lot about it. The CNCF said it's the number one of the top things for next year, whatever that means. But we'll talk a little bit about it. So chaos engineering. So chaos engineering is a discipline of experimentation on distributed systems in order to build confidence in the system's ability to withstand turbulent conditions. So another way I like to talk about it, it's the technique of proactively introducing turbulent conditions into a system to try to determine the conditions by which a system or service will fail before it actually fails. We learn before we encounter customer pain. And that's the great part about it, is that we're able to proactively experiment with the system and understand, ensure that the system actually still works the way you think it does. And to be clear, I have never seen a chaos experiment succeed the first time, right? What does that tell you? It tells you that, that's just one, that's my experience, but I think it's pretty synonymous. I think it's pretty unanimous, is that we're often almost always wrong about how we think our systems work. So chaos engineering, if you Google it on the internet, you're going to see lots of stuff about breaking things in production, and sounds cool, right? Like you'll see things about breaking things on purpose. These things couldn't be further from the truth, right? It's not about manifesting chaos. The point is your system's already chaotic. The idea is trying to establish order from the chaos through experimentation. So no chaos engineering talk would be complete without a Chaos Monkey story. So Chaos Monkey was born in 2008 during Netflix's cloud transformation process. Because a lot of people will come to me and they'll be like, Aaron, we can't do the chaos engineering. We can barely do the DevOps, or, we just started in the cloud, and I'm like, well, I mean, chaos engineering was born out of Netflix's cloud transformation. What they were doing is they decided to go from DVDs and data centers to the cloud and streaming. And during that process, so when they're building in AWS, AMIs were just disappearing. Poof, they would disappear. Right. The problem with that was it doesn't help to create stable services. So what they did was decided we're going to build our services to be resilient to these types of failures. So after they did that, they needed a way to test it. So they created Chaos Monkey. What Chaos Monkey does is during business hours, it will pseudo-randomly select a service that will bring down an AMI. Now, what did this do? The purpose of this wasn't to create chaos. What this did was it created the expectation for me as a service owner. If I'm building my service, is that I have to build. I have to expect that this failure is going to happen. This type of failure is going to happen. I have to build my service to be resilient to it. And what Chaos Monkey did is it sort of helped put a well-defined problem in front of these engineers. Turns out when you do that, they solve them. Engineers do pretty well when you give them good context and detail around problem. That's really where chaos engineering really helps. Is helps you provide more context about how the system actually functions to ensure what you're building will hit its mark. So it really helped accelerate Netflix's cloud transformation. So it's a key component. Actually, one of the biggest triggers for chaos engineering and right now that I've seen is cloud transformation still, believe it or not. So who's doing chaos engineering? I don't know. There's probably, I'd say closer to somewhere between 1,700, 1,800 plus companies. It's hard to keep track anymore. It's becoming sort of the next sort of thing. Chaos engineering was originally designed to be a tool set for SREs, because SREs you can't scale. They're humans, right? The idea is to create a series of tools to help SREs understand systems and build more safer and reliable services. So a lot of companies out there now doing it. Various levels of maturity. So there's also 3 books now. So originally, well, there's actually 5, but these are sort of the 3 ones I'm throwing out there. And this original Netflix book that Casey wrote, my co-founder. And then we just finished the official animal book, which is the one on the right, System Resiliency in Practice. That's got a chapter on security chaos engineering. I'll have a link to that at the end of this presentation, as well as the security chaos engineering book that's in the bottom there. And there'll be a link to that as well. That just came out last week. So getting back to it. So instrumenting chaos. So Casey and I like to loosely define sort of instrumentation into 2 buckets. This is to illustrate where chaos engineering sort of fits in this ecosystem, is that we believe testing is the verification or validation of something you already know to be true or false. It's a binary thing. You know what you're looking for before you go looking for it, and the purpose is to verify it, right? Whereas experimentation, we're trying to derive new information about the unknown things within the system, trying to understand what is the unknown, if you will, right? And we do that through experimenting. What we do is it's in the form of, I believe, if the X condition were to occur in the system, we've designed Y to be the response. And what you actually do is you instrument it. You actually execute that test. And really, this is not a build phase kind of experimentation like fuzzing or any of your other smoke tests, unit tests. You still do all those things. Do not confuse that. I'm not saying to do this. This is the post-deployment problem, right? Is that when you now have all these microservices and they're auto-scaling, they're connecting with other services. They're doing blue-green deployments, auto canaries, A/B testing. The complexity post-deployment is where the problem is getting more and more difficult. And when you have different sets of humans delivering on different sets of requirements on different microservices, and they're all interdependent, things are bound to go awry at some point. And that's why we write these hypotheses about how we actually believe the system to be working, and we execute them and determine whether we were correct or not. A few pitfalls with chaos engineering. It's not about breaking things on purpose. If you go to your management, or you start with a premise of breaking things on purpose, you might not have a job very long, right? It's not about that, right? What we're trying to do is we're trying to fix them on purpose, fix them before they cause customer pain, and that's really where the value is. That's why it's so attractive to a lot of organizations. So what is security chaos engineering? Well, this is an AppSec crowd, so what I'll tell you is it's no different, right? It's just how it's applied to the security we build in our systems. As a builder, most of my career, I kind of know how things are built, and I always look. I since the onset of getting into security, I've always looked at security being an engineering problem, right? And so I don't look at the system as its system and its security. I look at the system as being secure or not. And so this chaos engineering thing sort of made a lot of sense to me in that regard. And that's sort of how I was able to expand to sort of pioneer this space. So a common saying in chaos engineering is hope is not a strategy. It's not an effective strategy. It worked in Star Wars, but it really doesn't work in engineering. I mean, furthermore, engineers, we don't believe in two things. We don't believe in hope. We don't believe in luck, right? We believe in data. We believe in instrumentation, good instrumentation, better instrumentation, better. Tell me what's wrong. Give me context, right? That way I can build what I want to build, and that's it's important. So with security chaos engineering, what we're trying to do is understand where the inherent sort of weaknesses in the systems are before an adversary has the ability to take advantage of them. So what do I mean by that? Is that if you look at the majority of malicious code out there, I mean, as software engineers, we can read code and we can look at code, and most software security people were software engineers, I'm assuming. Is that if you look at most malicious code, I mean, there's about 5, 6, maybe even upward to 10%, for all I know, that malicious code that is actually sophisticated stuff. But the majority of it is junk engineering. It's junk code. It doesn't have to be very good code, actually, because usually there's sort of some sort of low-hanging fruit or that it's looking for, either like a misconfigured port or an open S3 bucket, or you name it. You can name a million of those types of vulnerabilities. But the idea is we're proactively trying to insert those conditions or inject those conditions in the system, determine whether or not the controls and the security we put in place to detect that low-hanging fruit can actually detect it before that we can actually detect it before an adversary can take advantage of it. That's really what we're trying to do. So, and we often misremember what our systems really are, and this happens because. And it magnifies, but it happens because accidents and mistakes are part of engineering. I mean, as an engineer, I will tell you, like, my process was, if somebody gave me something they want me to build, it was a process of, that didn't work. That didn't work. Oh, hey, that's cool. That kind of works. And then it's kind of, because, it's this, you're trying to, often as software, as engineers, we're trying to build things that never existed before. So it's a process of exploration and trying to figure out what's even possible, whether you can even build it or not before before you can make it secure. But in the process of doing that in a large scale system, is that it's easy to make accidents and mistakes, and those accidents and mistakes are part of what creates the low-hanging fruit, and we're going to expand on that. So really with chaos engineering for security, it's about continuously verifying that security works the way we think it does. And in doing so, we're able to reduce the uncertainty by building confidence in how the system actually functions. Here's some use cases. So these use cases are actually expanded upon in the Security Chaos Engineering O'Reilly book. There's some great case studies in there. Also, one from Capital One, as well as Cardinal Health on how they implemented security chaos engineering, as well as a couple tools out there. Anyway, the use cases that I found the most valuable when I started sort of pioneering the space were, I started with security control validation. I'm trying to verify that the security that I designed in the system actually got configured and placed correctly. And what I needed is a way to constantly ask the computer questions, the system questions, and to ensure that the controls were actually still as effective as I designed them to be. In the process of doing that, we started utilizing security chaos engineering for incident response. Incident response is a very valuable exercise for security chaos engineering, and because no matter how many people, how much money you have in your security program, how many security controls or fancy solutions you have to detect or to prevent, it's still a very subjective ecosystem. You don't know what's going to happen, what somebody's going to try to get in, how they're going to try to get in, who they are, and what their intent is. Like you're kind of waiting. All that preparation that you put in place, you don't know whether or not it's effective until the situation is designed for it occurs. So what we do with security chaos engineering is we proactively introduce the conditions that those controls are supposed to fire, when it isn't an adversary, and determine that proactively that it is effective before an adversary tries to exercise that condition. One of the interesting areas that a woman from Pinterest, Prima Barani, opened my eyes on was that being the ability to be proactive, you're introducing a controlled signal into the system in instant response, but also you're able to validate and verify whether the technology worked correctly, whether you had the right number of people, whether the run books were correct. But also, where she really did some experimentation at Pinterest is that on determining how effective the security logs were, is that when there's an active security incident, you're trying to figure out what the heck happened. You're looking for logs, looking context and data, maybe a SIM or security data lake or whatever it is. You're looking for that context, and if a lot of times the log events you'll get don't make any sense, right? And we're getting so many of them, and it's very difficult to do when you're under the gun, trying to figure out where an attacker is or what's been exposed or what happened. It makes it worse when you can't read the logs, But she was able to proactively introduce these events and sort of judge and value and grade how effective the logs were and how ready they were actually to respond to those kind of scenarios. I thought it was pretty valuable. And lastly, every chaos experiment in general, whether security or availability based, has compliance value. Essentially, what you're doing is you're proving whether the technology, the security worked the way you designed it for, or the way you documented it. All you have to do is keep the output of every experiment in a high integrity way and label it with the right control framework. And you got free compliance, audit material. So part of, like I said, the problem with its response is the response aspect. And like I said, it's a very subjective exercise. I think at United Health Group, when I was there, we had over 1,000 people in security. We spent a lot of money on security. But no matter how much we spent, how many people we put in play, we weren't perfect, right? And there's no way to be perfect. But what you need is, just like DevOps and continuous delivery, you have these feedback loops, right? Well, post-deployment, we need those feedback loops too, and that's really what we're doing. Is we're trying to ensure that everything's functioning the way it's supposed to, including the humans in incident response. Because it's very difficult to compare two different events, even though they look similar, because the context is different. Well, when you're actually proactively introducing these signals and events in the system, it becomes easier to sort of measure and manage the incident response process. And so what we're essentially doing is, instead of the post-mortem being the after-action exercise, the post-mortem becomes the preparation exercise. We determine how prepared we actually are for these types of events. So Chaos Slinger, this is the open source tool that a team and I wrote at United Health Group. It was the first open source tool to ever apply chaos engineering to cybersecurity, and talk a little bit about it. So Chaos Slinger, you can go out to GitHub, check it out. It's actually a deprecated project. I think United Health Group uses their own internal version now, but still, that doesn't matter. Actually, in the Security Chaos Engineering O'Reilly book, I go into sort of how you utilize it, as well as there's another tool called CloudStrike, not CrowdStrike, CloudStrike, that you can sort of model how to write experiments for. But Chaos Slinger's out there on GitHub. So when we were writing Chaos Slinger, we needed a good example that was relatable to whether you're a software engineer, whether you're a network engineer, a systems engineer, cloud engineer, and everyone kind of understands what a firewall is supposed to do, right? I mean, we've had them for a little over 30 years, and longer than that probably. I think of it. But anyway, misconfigured ports seem to happen all the time still for some reason. And I know what the reason is. It's because one network flow is not intuitive. Two, we're human, right? Meaning that people either didn't understand the change they were supposed to make, or somebody put the information in the ticket wrong, or got applied incorrectly. So this was a very easy thing that we expected to be able to cover for. What we expected to happen was that the firewalls we put in place would immediately detect and block the change, and it would be a non-issue. Turns out it's not exactly true, and we learned a lot from this experience. But here's the thing: this was something we expected to already to be a duh thing that we covered, and it did not to be a problem. But what happened when we did it was only about 60% of the time did the firewalls actually detect and block it. It was actually due to configuration drift issue between our commercial software division and our non-commercial software division, and we were able to discover this proactively, so we were able to fix that. But that was the first thing we learned. The second thing we learned was that the cloud-native configuration management tool caught the change and blocked it every time. So the thing we barely even paid for was more effective than the thing that we sort of expected to solve everything for us. So that was the second thing we learned. The third thing we expected to happen, so this is where I had a lot of doubt, is that we had our United Healthcare, we had our own. We had SIEM, but we primarily used our own tool, which is a large security big data lake type of solution. And I wasn't sure whether or not, since we were new to the cloud at the time, whether or not the alerts that alert would fire from the configuration management tool and the firewall. Well, it turns out that actually did. So I got some more confidence in the alerting and the logging. So we actually got the alerts. So that was the third thing we learned. The fourth thing, that we learned was when the alert got to the Security Operations Center, the analysts got the alert, but they couldn't ascertain which AWS account it came from. Now, as an engineer, you can say, "Well, Aaron, can't you just backtrack the IP address and figure out what instance it came from?" Well, yeah, you can, right? I mean, but that could take 15 minutes. It could take 30 minutes, right? And if SNAT is in play, you're going to have SNAT intentionally hides the real IP address. So it could be 15, 30, it could be 2 to 3 hours to figure that out. If this were an actual incident or war room, I mean, United Healthcare's a big company. They lose a lot of money for every minute that they're down, sometimes millions of dollars, right? But guess what? All these things that I'm talking about, we were able to learn proactively before they caused customer pain, before there was an outage, right? And before anybody worried about being blamed for not doing their job correctly. All we had to do was add metadata to the pointer, and it solved that problem. So that's kind of the premise behind what we're trying to achieve, and then, sort of the evolution of this is that this becomes an automation exercise, and you continually write more and more experiments, and then you expand in your coverage and becomes more and more of a regression test over time. And I'll leave you with one final comment, is that this is from John Allspaw. John Allspaw was the sort of one of the fathers of DevOps, as well as the father of resilience engineering for software. He's where I've learned most of my knowledge about resilience engineering, which is in safety engineering and cognitive science. Those are the things that's the deeper information behind why chaos engineering is so important, resides in those domains. But John likes to say, as engineers, we stop looking for better answers and start asking ourselves better questions. And I think as engineers, we have to really take that into stock. And that's sort of the end of my presentation. And I will leave a couple links. Here's the link to the Security Chaos Engineering book. I wrote it with Kelly Shortridge. She's pretty brilliant. And there's some good material in there. I'd love to give you feedback from anyone who has feedback. And here's a link to both books. So,
thank you so much, Aaron. Fantastic talk. Easily digested. It was. It's getting later in the evening, but it was easy to pay attention to, and it was easy to really grasp the concept. So, thank you for your time, and we'll just wait here for a few seconds and see if anyone has any questions. Abdullah, anything to add or ask or anything of that nature?
I'm sorry, I'm just posting in the the YouTube room to see if there's anyone that has any questions.
Yeah, I actually, that's a good point. I should actually say, if we seem awkward and slow on things, it's because we are actually pulling a lot of strings behind the scenes. So like clicking buttons and putting in links and doing things. So yeah. So,
Ken's operating me right now. So no, I'm just kidding.
That's how it works.
No, I mean, I'm trying to think. Like,
you've been involved in this journey for a while. I mean, you know, you've seen. I actually, Abdullah saw this presentation 3.5, almost 4 years ago at the DC, the Northern Virginia OWASP, like when I was still at United Healthcare. So
yeah, kind of the evolution of this.
Right.
It's been quite interesting. I mean, I guess to that point, then what's next? Is there a next?
So a couple different nexts. I mean, you know, I'm just because I'm the person that started this, you know, doesn't mean I know all the ways you can apply it, all the ways you can utilize it. You know, Capital One does it. They call it cyber chaos engineering. Cardinal Health calls it applied security is what they call it. You know, but it's but they're applying it different ways that I've never applied it before. I mean, and it's kind of interesting for me to see when people pick it up from like blogs that I wrote and the open source tool, right? Like, but it's kind of cool to see it evolve, and I really enjoy when people reach out and share the stories. So in the Kelly and I are writing the full Riley book for next year. And we're capturing more and more case studies and, you know, going deeper on like the management aspects of it and the engineering. So like in this one, O'Reilly really didn't. I had a lot of code examples and scripts and things like that. And O'Reilly's like, that's too deep to start with. I'm like, well, you know, as an engineer, I want practical like how to, right? Like, you know, but in the next book, we're really gonna expand it and all that area. That way people, but really, I mean, it's not that hard if you know Python or Bash to really write a lot of these experiments.
Right. Yeah, I think that would be interesting. I think, you know, for a talk, what I would really love to see is like practical examples of like the chaos engineering in action. I was specifically security chaos engineering in action. That would be really neat to see. Yeah, I think that would be super neat to see.
Well, I'm planning some of that with David from Capital One. We're going to do some of that, some examples on how they do it.
Okay.
A lot of people are doing it. It's either on the cloud, and usually with AWS, or it's Kubernetes, or it's containers in general. Okay. Even though you have Twistlock or Aqua, it doesn't mean that they're always configured correctly, that they're not drifting from the environment, or that they're even enabled on those instances. And you know, I found that was really interesting. That I think it was Cardinal Health that was finding out that the tools are great, but they just weren't being implemented and weren't as effective as they were supposed to be. So
that makes sense.
Yeah,
makes sense. Great. Thank you so much. Appreciate it.
No worries. Thanks for having me.